Hi, this is the full Cactus tutorial. You can get the files from the first comment. This tutorial is meant to be for beginners, but you need to have some basic Houdini information before you start digging into it, so keep that in mind. So first we need to start with a simple line. You can just increase the point here, or we can create an adaptive point distribution using a ramp, as you can see here. What I'm doing here, basically, I'm taking the P box, which is the bounding box. So if you don't know what is a bounding box, you can take any geometry and plug it into the back of a box, and you will get a bounding box. So what we are doing here, we are scattering point based on an attribute, and that attribute here is called density. And we are generating an attribute using the bounding box and the function relative to point bounding box, feeding it with the current geometry and the point information, and creating a ramp function to control the point distribution according to a ramp, giving it a name, and feeding the ramp parameter with pbox y, which is where we're going to scatter the point vertically on the line. And then we are exporting a variable vector attribute density. So v is for vector, and at is for attribute, and density is the name of the attribute. So the script, by the way, you need to create spare parameter, and you need to shape the ramp accordingly. And after that, you need to make sure that the line has more than, preferably have maybe 10, 25, the first line. Now we are plugging that attribute into the scatter, point scatter. Density, it can be a different name if you want. And I'm controlling the amount of point from here, force total point. So you can play with the setting, but this setting is not what's going to work best, I think. Now we have a ramp controlling the, like we're scattering point according to a ramp, as you can see. For us to get the top profile of the cactus, we're using, first we created a grid, and after that we are using this attribute triangle running over point. We are using relative to bounding box, and we are using a signing the point on the x-axis. After that, maybe this is more obvious. Tell me down in the comment, do you want to see the script this big? So we are signing the point on the x-axis, and then we are using the ramp, and we're using a float value overall scale, and the sign we created here to get the new x mirrored. We're using the sign to get it mirrored. We're using the ramp to control the shape using a ramp, and we are using the channel float to control the overall scale, and we are assigning everything to the new x. Now what does that look like? So as you can see here, this is the top profile shape. We can control what the shape looks like, and we can control the width of the cactus. So from a simple grid into a function that control, or like an expression controlling the shape using a ramp, then we are mirroring the grid so you can get. And then we are using polyfill with a batch group so we can isolate the batch group, and we are, so I'll show you here. If we did not create the batch group, basically it's not going to work out because there's so many segments for the skin node to work out. How we are isolating the batch group, we have a blast node, and we plugged the group batch here, and delete not selected. This way it's going to delete everything but the group selected. Then we are going to add a copy to point, so we can copy the shape to the points on the right and the shape on the left, and then we will add a skin node so we can create a geometry from that. We're using group of n primitive, and this is actually going to be the number of points. So we go here, we copy parameter, and here we paste relative reference. I just have it fine. Now the amount of point is controlling it's a little bit broken actually. So it's broken because we did not sort out the point. It's not connecting them in the correct order. Now like this, they are being corrected. So what I have a sort node and I have point sort by Y. By default, it's set to no change. So you know that. Now we can control the shape on the top, but we need to also be able to control the shape on the front and side. Now, how we can achieve that? We basically are creating a third B box with another attribute triangle. This time, we're also using the Y of the B box with the ramp, and we are using a scale or a scalar on the X and Z, one for the width and one for the length. And we are exporting an attribute scale. I played with the ramp until I got the right shape, and this is a scale, as you can see. I also played with it a little bit. Now what I'm doing with the last few nodes, the reverse is just to reverse the normals, because when we skin them, this is inverted. You can put it here if you want. And we are filling the top and bottom, and we are creating a batch group here. We are using a polyfill node, and then we are using a group keep by normals, and we are grouping only the bottom by this setting. Basically it's direction -y enabled, and spreading angle is 3. I think you can set it lower too. Now we can only remove the bottom and keep the top, so we can create the top hat group. So to create the top hat group, we need to create the group expand, and we need to restrict by normal, and we restrict by normal, play with this until you get the right, and we can play with steps too, so we can get the top hat group. So this is very important for us for later, because this is critical for the scattering and the branching. Now just to think here, the base group here is the batch group, the one we created when we added a polyfill, and here we are subdividing so we have a nicer shape. Now to create the point, what I'm using here, I'm using the exact setup as before, a line but without adaptive distribution, using a ramp and a circle, and I am creating the shape. I think skin is just used, and I'm only keeping point by using add. I'm twisting to simulate the Philiatox pattern, and I'm using ray to project the point back into the pedal, and I'm using relax to relax them a little bit. I'm using normal too here. I'm using fuse to fuse any close by point. And as you can see here, we have point, but we are not going to actually copy to point here. What we are doing, we are going to copy to point later. So what we are doing here, going to merge, and this now contains the point. What I did with my original setup, I created a much complicated script that is actually not very necessary. But an important point here, I'm only using the length, shape, and the reason why I'm using this, because we can map this parameter here and get more consistent result with the cactus shape itself. So you know, you can actually skip these three. We can skip them using a sweep and a line, and sweep contains a ramp, because this is one dimensional and the shape is 2 dimensional, and we need it 2 dimensional so we can twist the shape, so you know. So what I mean with one dimensional, that I'm using the exact same expression we talked about earlier, but I'm only using the length, and I'm only mapping the length here, so it's only being controlled by one ramp. There's quite few different ways to get to the same exact result. I'm just using the exact setup I used earlier, so I can have the system more consistent with each other, because it's a procedural system. So here you can copy parameter and paste relative reference, so it can be the exact same. And you can plug also the line here, so we can get the same height, so you can make it more procedural. Now for us to create the actual spikes and to create the base of the spike, now here I have a sphere, small one. I'm squishing it a little bit and clipping it using clip, and I'm poly reduced. It's going to have so many polygons. Then I'm copying to point. Here it's directed on the x-axis, positive x. And to create the spikes, first I'm instancing the points. So each point now has 5 points on top of it. I am randomizing the normal, adding, and I am setting the B scale between 0.4 and 1, and I'm copying to point to create lines, copying line with a color. This is the lab color gradient, and this is just a line that is facing the Z. Again, when it comes to copy to point, everything has to face the Z. And then I'm sweeping after copying to point, and the sweep contain a ramp, as you can see here. And only 3 columns because there are so many of them. So it's like everyone is basically a triangle. And we merge everything together to get the final, not the final, but the semi-final. Now to create the branching system, first we need to group. We need one group to group the spikes point and one group to group the base pedal, and we can group them in one group. Now here I'm switching between a few different points and one point pointing up. Why do we need a one point or few different points? We can switch between one branch, base branch, and 3 or as many as we want. This is the whole purpose of it. So the one single point, I just added an add node to 0, 0, 0, like just adding a point, and I'm using the attribute triangle to add normal pointing up and B scale to 1. And when it comes to the branching point, I have a sphere, and as you can see it's a little bit squished. I'm clipping it, and I'm clipping it another time. One time in the middle and one time on the top. I'm adding normal. I'm scattering point. Now we have points and they have normals. And we are flattening the y by just typing at b.y equals 0. And I am doing an attribute randomize so I can lift the point a little bit, and I can control how much lift I want to have. And I'm adding another attribute randomize so I can get a little bit of a randomness. We can also, if this is add, we can add 0 here, as you can see, just randomizing it a little bit. We can control that also with the global scale. Finally, I'm adding a B scale attribute randomize. So the attribute name is B scale. Here the attribute name is N, which is normal, and it's from 0.7 to 1.1. So the cactus is going to have a varying sizes here. So for the core loop setup that is going to scatter the system, I'm basically creating a loop blasting the top hat group that we created earlier, creating another loop, looping for each and every single one of the top hat group, scattering, and after that I'm copying to point. I'm copying the same one that we've seen before, but it is on the z-axis. It's aligned on the z-axis, but we rotated the x-axis. Yeah. And here the only thing you need to know, we go to the block end and we merge each iteration. We need this active, and that will give us actually the last iteration only going to give us the branches, and we can merge the base first branch. And as you can see here, we can switch between single branch and multiple branches that will control the look and feel of the cactus. By the way, you just type in for loop, and this is the first for loop. You merge each iteration and set it maybe to 2 or 3. And for the second for loop, you need for connected pieces. So we have first and second. This is the second one, this is the first one, so you know. So this is the most complicated vex script in the entire tutorial. We're controlling the branching using a ramp on each iteration, and we are using that. We're fitting iteration, which is the current iteration number, between 0 and the total iteration number, and 0 and 1, and we're plugging that into the RAM that controls the branching, and we're plugging that into a RAM that controls the B scale. We're outputting the B scale, and we are creating a minimum and maximum branching. And here I'm taking the current iteration, but this is like the spare input. This is the second input. I'm going to show you the input now, just in a second. And I am fitting this ramp with a random seed, subtracting the current iteration to get a random number with this. And this is giving us a random number between the parameter minimum and the parameter maximum, and then supporting all of that to rand number as detail attribute. So here we have maximum number of cactus that can exist per branch, and the minimum number of cactus that can exist per. And here we have the ramp that controls the amount of branching using a ramp, so we can get a little bit of an artistic control. So we can, let's say, get much less branches on the top and much more branches in the bottom, or vice versa if you want that. But this system overall doesn't really work very well if you want to have too many branches, unfortunately. Maybe 3. So it's 1, 2, 3, and 4. You can have 4 branches at max before start breaking the system. Now after that, I'm plugging the detail attribute I just created into the scatter. And this is looping. So this is going through for each connected pieces and going through for each connected pieces scattering point and doing that. And for the input, I basically have a spare input, and I'm plugging this to the spare input, and I have the metadata plugged into the second input. So it's basically controlling the iteration from the first loop, and it is taking the current iteration, which is it is randomizing your current iteration on each connected piece here. Did you understand this complicated system? This is the most complicated part. And after that basically we're randomizing normal, and we are exporting the scalar, and we are also randomizing normal, but as before we are selecting direction and orientation and making it orient up. So any plant or vegetation going to be somewhat, I'm going to show you in a second, any plant or vegetation going to be somewhat directing itself upward, trying to follow the sun, trying to get that sun rays and sunlight. And then I have some random rotation. Then I have random rotation. What I'm doing here, I am creating a rotation angle, which is 400. It could be 360, it could be 200. So as you know, the 100% rotation, which is going to rotate an object back to its original state, is 360. And I am creating a random number between seed and point number and 0, between 0 and the maximum rotation. This could be negative number, this could be negative 200. Anyway, I am outputting a rote, which is, I believe, a built-in attribute using a quanterion, because quanterion are used for such job. And random rotation, this is a variable created here, and I'm plugging the normal so the function would work, but the overall rotation attribute is rot. After that, I'm randomizing B scale between 0.4 and 1.4. You could have between two values. It's one dimensional, as you can see here. B scale is one dimensional, normal is 3 dimensional, because it's a vector, if you did not know already. Then, this is interesting, because if you remove this, it's just going to have much more chaotic branching. So here what I am doing, I'm randomly selecting percentage of the point, Here I'm selecting percentage of the point, and here I'm grouping this. I'm exporting a group for when a point is at a certain p scale. So when the pedal at a certain p scale, or it's small enough, it will be added to this group. And then after that, after adding it to the group, I am actually adding it to another group. These two can be done in one. We can just remove, instead of setting to group, we can remove that. Anyway, after that, I am blasting the group, which these three can be done in one node, attribute triangle. I was learning about that. I did not know, or I knew probably, but I was too lazy to implement it. Anyway, after that, I am doing this part I showed you before. Just copying to point, and then this is basically isolating the last branch. I am taking the iteration number, and I'm saying if iteration number equals total iteration number -2. Actually, this is giving me, if it's -1, it's going to give me the last. If it's -2, going to give me the one before the last. If that make any sense? As you can see here, yeah, it's actually blasting. No, actually, it's giving me the last. Nice. I'm doing this to be able to scatter the fruit on top of these later. So basically, this is the setup. The only thing I'm going to cover in a second, actually, the color and the color of the point thing. By the way, to split the group, we use a split node, and we can plug either the point group or the other group. So you know, forgot to mention this. So to get the points to give me these radial gradients, I'm using an attribute transfer. I'm using the point with the white color and the black with the pedal with the black color, and attribute transfer, transferring point color attribute with these condition, and I'm getting this, and I'm remapping the attribute color to the color dots. And here in the attribute Bob, I'm using the main color, which is an attribute, the gradient, and the color randomized peer connected pieces. So here how I did it. So this is before randomizing the color, this is after. I'm using class, and I'm using connectivity to get the class attribute, so I can get each connected pieces. I'm doing I have the attribute randomized as CD, and I'm randomizing with these value and dimension 3 because it's a color, which is a vector, and I'm renaming attribute renames color into color main. And here I'm using a bind to view it first. Here I'm using the main color, and the dots are the radial gradient from the points, to multiplying them together to get this look. This is basically how I got the color. And for the first, let me see here. All I have here is a lab gradient, but you don't have to have a lab gradient. You can have a VOB, point VOB, So you can have a VOB, and instead of having the lab gradient, basically what you need to do here, you need relative to bounding box, again, vector to float, and selecting 2 will give us Y, selecting 1 will give us X, and 3 will give us Z, and we plug that to a ramp, and we plug a ramp into the CD, which is color, and after that we can have a gradient without but the lab tool are actually very important. I suggest you have them, but just in case if you wanted to do more procedural colors and texturing, you don't even have to have an extra node. So this is the full tutorial. I hope you like it. Tell me down in the comment what do you think, and if you want me to cover something else in Houdini. This is a beginner friendly but somewhat difficult for beginners, so I hope you enjoyed it, and I hope you consider subscribing.